continuous time and discrete time signals. Examples and mathematical representation. Signal may describe a wide variety of physical phenomena, although signals can be represented in many ways. In all cases, the information in a signal is contained in a pattern of variation of some form. For example, consider the simple circuit in figure 1.1. In this case, the pattern of variations over time, the source and the capacity voltages Vs and Vc are examples of signals. Here, a simple RC circuit, figure 1.1, a simple RC circuit with a source voltage Vs, capacitor voltage Vc. Signal. This is the signal. In the figure 1.2, an auto will respond to an applied force F. This is the applied force from the engine and to a retarding fractional force rho v proportional to the automobile velocity. The variations over time, applied force and the resulting automobile velocity v are signals. This is the signals. V are signals. Here signals Vs and Vc are the examples of signals. This is the signals. Okay. And 1.3 examples of recording of speech in 200 milliseconds. Here one type up to here. Okay. So from here to here different, here different, here different. The signal represents acoustic pressure variations as a function of time for the spoken words. Should we chase the top line of the figure corresponds to the word should, the second line to the word we, and the last two lines to the word chase we have indicated approximate beginnings and endings of each successive sound in each word. Another example, consider human vocal mechanism, which produces speech by creating fluctuations in acoustic pressure. Illustrations of a recording such a speech signal obtained by the speech signals. Using microphone to sense variations in acoustic pressure, which are then converted into electrical signal, as can be seen in figure. Different sounds correspond to different patterns in variations of acoustic pressure, and the human vocal system's pressure intelligible speech by generating particular sequences of these patterns. Alternately, for the monochromic picture shown in figure 1.4, this is monochromatic picture. Okay. Is the pattern of variations is brightness across the image that is important. Brightness. Yeah. Also okay. Signals are represented mathematically as functions of one or more independent variables. Signals also are represented mathematically as functions one or more independent variables. For example, speech signal can be represented mathematically by acoustic pressure as a function of time, and a picture can be represented by brightness as a function of two spatial variables. Here, typical height speed, typical and annual, vertical with wide profile. Here an example of a discrete time signal. Here date. Graphical representation of continuous time and discrete time signals. This is continuous time signals. Here is the discrete time signals. Graphical representation. Continuous in a x-axis time, y-axis x of t. How much? Here how much? Here how much? Here how much? Here 0 t. This much. This much. Same like this in discrete time signals. Signal and signal energy and power. Signal energy and power. P of t equal to V of t into I of t equal to 1 by r v square of t. Total energy expended over time interval t1 to t2. T is the time interval. Here closed interval. T1 is less than or equal to t. T is less than or equal to T2. So in between T1 to T2, Pt of Tt equal to T1 to T2 1 by r v square of Tt. And the average power over this time interval is 1 by T2 minus T1 integral over T1 to T2 P of T dt equal to 1 by T2 minus T1 integral over T1 to T2 1 by r v square of t dt. Here integral over T1 to Dt mod x of t mod square dt. That is, this mod x denotes the magnitude of the possible complex number x. The time averaged power is obtained by dividing equation 1.4 the length t2 minus t1 of the time interval. Similarly, the total energy in a discrete time signal x of n over the time interval n1 is less than or equal to n is less than or equal to n2 is defined as summation over n equal to n equal to n1 to n2 mod x of n mod of whole square. And dividing by the number of points interval n2 minus n1 plus 1 yields the average power over interval. It is important to remember that the terms power and energy are used here independently of whether the quantities in equations 1.4 and 1.5 actually are related to physical energy. Nevertheless, we will find it convenient to use these terms in a general fashion. E here E infinity equivalent of definition limit t tends to infinity integral over minus t2 plus t x of t mod square dt equal to minus infinity plus infinity x of t mod whole square dt. And in discrete time it is available e infinity suffix infinity equal definition limit n tends to infinity summation over small n to equal to minus n2 plus n x of n mod whole square equal to summation over n equal to minus infinity plus infinity mod x of n whole square. Note that for some signals, the integral in equation 1.7 might not convergence. Even x of t or x of n equals non-zero constant value for all time. Such signals have infinite energy, while signals with E infinity is less than infinity have finite energy. In an analog spectrums, we can define the time average power over an infinite interval as P infinity, the equivalent of limit t tends to infinity 1 by 2t integral over minus minus t2 plus t x of t mod whole square dt, and P infinity, the equivalent of limit n tends to infinity 1 by 2n plus 1 summation over n small n to minus capital N plus n mod x of n mod whole square in intervals and in continuous and time discrete time respectively. With these definitions, we can identify three important classes of signals. The first these are the classes signals with finite total energy, that is, those signals for which E infinity is less than infinity. Such a signal must have zero average power. Since in the continuous time case, for example, we see from equation 1.8 that P infinity equal to limit t tends to infinity E infinity divided by 2t equal to 0. An example of finite energy signal is a signal that you take on the value for 1 for 0 to 1, that is the t is in between 0 to 1. 0 is less than or equal to t, t is less than or equal to 1 and 0, otherwise 0. Okay, in this case E infinity equal to 1, P infinity equal to 0. Yes, second class of signals are those with finite average power P infinity, B infinity. From we have just seen if P infinity is greater than 0, then of necessity E infinity equal to G infinity. This is of course makes sense since if there is non-zero average energy per unit time, that is non-zero power, then integrating or summing uh, this is over infinite time interval yields an infinite amount of energy. For example, the constant signal x of n equal to 4 has infinite energy, but average power P infinity equal to 16. There are also signals for which neither P infinity or E infinity, neither P infinity nor E infinity are finite. A simple example is the signal x of t equal to t. We will encounter other examples of signals in each of these classes in the remainder of transformation of the independent variable. Yes, central concept in signal system analysis is that of the transformation of a signal. For example, in a aircraft control system, signals corresponding to the actions of the pilot are transformed by electrical and mechanical systems into changes in aircraft thrust or the positions of the aircraft control surfaces, such as the uh, radar or ailerons, which in turn are transformed through the dynamics and kinematics of the vehicle into changes in aircraft velocity and heading. Also, in high fidelity audio systems, an input signal representing music as recorded